Since membership in a set can be thought of as a proposition, element X belongs to set S if P of X, the defining property for our set, is true, I want to be able to parallel the logical operations we did with set operations. It's going to look awful familiar. So let's suppose I have two sets. Or even just one. I can think of all of the logical operations we did. Let's start with the base 3. I had a negation, I had an and, I had an or. Let's turn those into set ideas. So I have some set A in some universe of discourse, whatever it is we're talking about, numbers, people, books, whatever. I am going to define the complement of A Sometimes you will see this written as a prime. Sometimes you'll see this written as a bar. Depends on the textbook you're looking at. This textbook uses A with a little C up above. Then my complement is the set of X that are in U that are not in A. Remember that little element symbol, this little funky E thing, means belongs to. X belongs to our universe, but it doesn't belong to the set A. So if I go back to the set of letters, we defined the set of vowels. Well, then V complement is the set of all the consonants. There. It's all the rest of the alphabet. But that's literally the negation in logic turned into a set ID. The set of things that are not part of A, that are still part of the universe we're talking about. We had a Venn diagram for a set, right? A circle inside the box that was our universal set. So if I have our universe and our set A, what's the complement? Oh, it's everything outside of A. But we still have to be in this particular universe, so we still have to be in the box. Questions? That's the only unary operator we have. All the rest were at least binary operators, right? And, or, if, then, all of those. I should be able to do binary operations as well. I just need two sets. So let's suppose we have A and B sets in our universal, whatever it is. I want to do A and B. So my definition for this thing is going to be the set of X's so that X is in A and X is in B. We're going to call this the intersection of two sets. And the symbol for the intersection is this kind of upside down capital U. It's basically a rounded off version of the and symbol that we were using before, the conjunction symbol. And if I want to do an or, just like I would turn the and upside down, I'll turn the intersection symbol upside down. We'll call that the union of our sets. So I have an intersection and I have a union. If I'm looking at a Venn diagram, I have my universe, I have my two sets. If I want the intersection, I need the things that are in A and the things that are in B. Now, here's where I need to be persnickety. I need the same X to be in both sets, right? So that means the X has to be in A, it has to be in B. It can only exist in this little section. This is the intersection of our two sets. But if I want to do OR, well, this is an inclusive OR, right? That's what our symbol is. Inclusive means it could be in one, it could be in the other, it could be in both. Well, that's everything. Here are two sets. What's the union? What's the intersection? They're just sets of integers. Evan? Yeah, as far as I can tell, that's the only number that's in both, right? It's just 3. So A intersect B is the singleton set containing 3. The union, on the other hand, contains everything that's in both sets. 1, 3, 5, 7, 9, 2. I already wrote down the 3, 4, and 6. Remember, a set is unordered. It does not matter what order these elements appear in. They also don't only have to be written once. I could have written the 3 down twice, couldn't I? But if I am counting size, cardinality, well, then I have to be careful, because the definition of cardinality says we count distinct elements, right? So I can't just say the number of things in A union B is the number of things in A and the number of things in B. I would have counted my 3 in there twice. That's not allowed. If I count it twice, I really only want to count it once. I should take one of those counts out. So if I want to count the number of things in a union, I need to count the number of things in the first set, and I need to count the number of things in the second set and add those together. But I need to make sure I remove everything I double counted. In this case, I'd be double counting just the number 3, but in general, I'd be double counting whatever was in my intersection. If I go back and I look at the Venn diagram, I counted all the stuff in that shaded area when I counted it for A. I counted it again when I counted it for B. That's counting it twice. I only want to count stuff once, so pull it out. With small sets, this is direct. With large sets, this gets a little more complicated, but it's just a counting. If I have more sets, this idea still works, but I have to be careful and count them really deliberately. More on that in chapter 8. This is called the inclusion-exclusion principle. And the version in chapter 8 is the general inclusion-exclusion principle. I'm going to give you a new term. Two sets whose intersection is empty are called disjoint sets. The intersection of my two sets is empty. They have nothing in common. They still have to be within the same universe. If I've got two sets, they don't overlap at all. Wait a minute. They don't overlap at all. What's the Venn diagram look like? Talk to me, Colin. Two separate circles, no overlap. If I do have an overlap, well, then that's A intersect B. What about the other part? Let's go back to where we had an overlap. I want to do a set idea of subtraction. A take away B. Sometimes we actually use a minus sign. Some textbooks just use a backslash for this. So you'll see this in two different ways. This is sometimes called the complement of B in A. Okay, well, wait a minute. Complement means things that aren't, yes? So the complement of B in A. What part should I shade in to make that work? The complement of B in A, it should be part of A, right? But it should be all the parts of A that aren't B. So what we're going to do is we're going to define this as the set of X so that X is in A and X is not in B. And yes, that's this part, but not the intersection. Sometimes rather than the complement of B in A, it's the complement of B with respect to A. Again, different textbooks will call it different things. Questions? I have an and, I have an or, I have a not. If then. We could do if then by writing the negation of an and statement. Back in chapter 1, section 3, we had all of those logical equivalences, right? Big table. I told you it would be a good idea to have somewhere because I don't want you to memorize it. The and is the opposite of an arrow. I can turn an arrow into something that's just negation or, okay, I can write these without ever using the arrow. That means I can define if then in set terms. I can define if and only if in set terms because I have this characteristic right here. So there's a way to do all of the things we do in formal logic, starting with sets and deriving logic from it. The definitions I'm giving you are using logic to define sets. So, depending on whose view of the universe you like better, you can say, I am going to derive everything in mathematics starting with the ideas of logic. People like Zermelo and Frankel derive axiom sets of postulates and then said everything's going to follow from here. People like Russell and Whitehead started with sets and said, I'm going to derive everything from here. And they both showed that they were exactly equivalent ideas. So the foundational rules in mathematics I started with logic. Whitehead and Russell said, no, we're going to start with a set. Something is in or not. Then I'll make everything follow from that. And that means that all of those crazy ideas about logically equivalent sentences and truth tables and all of that stuff, they have exact parallels in sets. Page 140. If I go back and I look at all those logical identities in chapter 1, section 3, where we had the double negation, right? Not A is this, not P is the same as P. Not A is the same as A. The double negation becomes the I can talk. Complementation. It's a double complement, right? Instead of double negation. Because what complements do for sets is what negation does for logic. A and true is A. A or false is A. Those were the identity laws for propositions. Here they are written in set terms. Every one of these rules comes across exactly the same way as our logic rules did. Even my buddy De Morgan. The complement of A intersect B. Well, that's not A and B. That's not A or not B. A complement or B complement. Those are the same rules. Hot damn. So if I wanted to show, that was something we did with the truth table, right? We showed De Morgan's laws work by creating a truth table. I want to show something like De Morgan's laws here. How would I write De Morgan's law? This is our De Morgan's law written for sets. That's one of them. I'd like to prove that this is true. We talked about proving set equalities on Monday. What did we say back then about proving sets being equal? That would have to, but I don't know what A and B are, right? I don't know that they have any elements at all, right? There was something else I did that was specific about talking about equals. It was related to the idea of subsets. But I like that they contain the same thing, so I may have to work on that. What was the idea about subsets? To show that A equals B. I've written S and T this time because I'm using A and B already. I promise I wrote it down on Monday. And if I wrote it down, you should have too. If not, go back and look at my scanned notes on Canvas because we have them there. Huh?
References for two sets in the same universe, A is a subset of B if all of the values inside of A are in, or, yeah, are also part of B.
That's the definition of a subset. That's what it means to be a subset. A is a subset of B if all the elements of A are also elements of B. But I want to show they contain the same elements, right, Gracie? Talk to me. Aha. So I need to show that the first is a subset of the second and that the second is a subset of the first. So in order for me to do this, I have to do two proofs. I have to show, as you said, Colin, it's a subset. I have to show that anything that's in this thing is also in here. But then I have to do it the other way. I have to show that anything in this thing is in here. So it's kind of like an if and only if, right? Because that's what an equal sign is. You're in here, if you're in there, if you're in here. So the if goes both ways. So I have to do two proofs. So let's pick one direction. I'm going to first show this direction. I haven't shown it yet, but that's what I'm going to try to do first. So that means I'm going to pick something in this set. Let X belong to this set. But that's a complement, right? And if it's a complement, that means that X does not belong to A union B. Now, clearly that means X can't be part of A. Since A is a subset of A union B, right, Colin? That's our definition of subset. Everything that's in here has to be in here. Since A is in there, this sentence means X is not part of A. The following is the most important word in this proof, this part of this proof. And since B is contained in the union, what can I say?
X is not part of B.
Hey, wait a minute. Therefore, X is not a part of A and X is not a part of B. What's the symbol for and in sets? The intersection symbol, right? But if you're not in A, what are you in? If you're not in A, you must be part of same thing for B, right? Hey, look, it's in here and it's in here. That means it's in their intersection. Now, Grace, I've only shown one side, right? Colin, by the definition of being a subset, I picked an arbitrary element in here and it ends up in here. Universal generalization. If it's true for any X, we just picked one, then it's got to be true for all of them, right? And that means that every X that's in here is in here. That's the definition of a subset. So a union B complement is a subset of A complement intersect B complement. This is check mark number one. If I start with something in the left set, click, 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 proof, 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 I end up with something in the right set. Now I got to go backwards. Part two. I want to show it this way. So suppose X is something in A complement intersect B complement. The word complement means and, right? I'm sorry, not the word complement. The word intersection means and. Got to say the right freaking thing. Jumble up my sentence like that. The word, the little bar means complement. This means and. Therefore, X is in A complement and X is in B complement. I'm basically going to work the same set of sentences we wrote down exactly backwards. If you are in A complement, then you must not be in A. And you must not be in B. You ready for my buddy De Morgan? I've got a logical sentence here. Therefore, not X not in A or X not in B. Wait, I put the parentheses in the wrong place. Stop, I wrote it wrong. Not X not in A. That needs a negation as well. Or not X not in B. That's the regular logic version of De Morgan. P and Q is not P or not Q. That's what De Morgan's law says back in chapter 1. Wait a minute. If not X not in A, what's that the same as? This thing right here. Not in means you are in. Or X is in B. Wait a minute. That's a logic statement. Turn it into a set statement. What is a set? Is X a part of? What single set can I write there? Well, combined set. But or in set terms is that union symbol. But if you're not in a particular set, you must be in its if you're not in the set, you can't be in the set. You can't be inside something in the set. If you're not in the set, you're outside the set. What's the outside called? Starts with a C. The complement. X is in A union B complement. Hey, wait a second. Wait just a blinking second. I started with something in here, and I ended with that thing must be in here. And we picked an arbitrary thing, right? If it's true for an arbitrary one, it's true for all of them. And that means that everything in A complement intersect B complement must also be in A union B complement. This is check mark number 2. And that means that I've shown everything in this set can be found in here and vice versa. Back here. Now, I am the first person who will tell you that I would have rather given myself a root canal than work through that. That was disgusting. but I still need to prove things about sets. When I proved that things were equal logically, I could do it by using all of those logical equivalences, right? But I didn't. What did I do instead when I wanted to show things were equal? In logical terms. Then I definitely can't show they're equal if you're telling me to show they're not equal.
I proved that there.
So do a proof by contradiction. But that wasn't what I did with logical sentences. I did that with theorems and claims and things like that, but with logical expressions, P and Q or R is equivalent to something else, right? How did I do those? I did truth tables. I want a truth table version for this. The truth table version is called a membership table. For every set we've got, something is either in the set or it's not in the set, right? So I'm going to build a table with all the possible options. And each option is either going to be a 1 or a 0. It's a 1 if the thing I'm using is in the set. It's a 0 if it isn't. We only had 2 sets, A and B, right? Draw me a Venn diagram for 2 sets that have potential overlap. Inside the box, how many bounded, distinct pieces are there? If I took this picture and put it in paint for you on your MacBook and asked you to use the little paint dump, how many times did you have to dump to turn that whole thing black? 4 times. For each one of those 4 pieces, I want you to write 2 numbers. Is this piece part of A? Is it part of B? Then it gets not in A, not in B. What about this piece? Is that in A? Is it in B? What about this piece? What about this piece? Ready for this? No matter which possible X value you pick, one of those 4 is true, isn't it? Those are all the possible membership options. Replace 1 with T and 0 with F. What do you get? True, 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 false, false, true, false, false. Son of a bitch, it's the same thing. That's a truth table. But the thing I'm asking about truth is, are we in the set or are we not in the set? Am I a member or not? If there's a 1 there, I'm a member of A. If there's a 0 there, I'm not a member. Same thing for B. But now I can build all of these other things. So we were trying to prove that A complement intersect B complement is equal to A union B complement. I'm going to build the left-hand side and the right-hand side one at a time. So I have A, B, 1, 1, 1, 0, 0, 1, 0, 0. So I start every one of these just like a truth table. Now, do you want to do the left side first or the right side first? Okay, then I need A complement. Well, complement just means flip it around, right? It's not A, 0, 0, 1, 1. B complement means flip it around, 0, 1, 0, 1. A complement and B complement, because that's what the intersection means. It means and. The only thing that should be true is when both are true. I'm using an and. Both are true in the bottom row, and only one or none is true in the top rows. Go back and look at the Venn diagram. If I tell you you are an A complement intersect B complement, that means you need to color everything outside of A. You need to color everything outside of B, and you need to take where those overlap. Isn't that going to be the section that we call double zero? This is the left-hand side. Now let's do the right-hand side. The right-hand side starts with a union, A or B. What is the appropriate column for A or B? True, 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 false, right? 1, 1, 1, 0. Now take the complement of that, because the right-hand side is A union B complement, and you get
0, 3.
And lo and behold, those two columns, they match. Technically, I should write one more column. Are those two columns equal to each other? And I will get 1, 1, 1, 1, a tautology. I like doing truth tables, so I like doing membership tables a whole lot more than I like logical equivalences, than I like set equivalences. This works so much nicer, in my opinion. Questions? Everything I've done for 2 sets works for more. So I can have A intersect B, right? That would be these. I can have A intersect C. I can have B intersect C. What's this little middle triangle thing?
They all intersect each other.
A intersect B intersect C. I can then use complements and intersections and unions in 3 of them. That works. I can use my ideas to generalize all of those rules from 2 to 3 to as many as you want. I can do the numbering again, can't I? So I would have outside, this would be 0, 0, 0. And this would be 1, 0, 0. And this would be 0, 1, 0. And 0, 0, 1, right? If I'm writing them A, B, C, I've put them in an order. The very middle. What's the very middle? And then all of the others have 2 1s and a 0. 1 1 0, 1 0 1, 0 1 1. 8 distinct options. P, Q, and R gave me 8 distinct rows. T, T, T. TTF. TFT. TFF. They're all the same pieces. Just instead of T's and F's, I've got 1s and 0s. Therefore, I could try and do more. If I try and draw a Venn diagram with 4 sets, I run into a problem. If I try and do it with 4 circles, I won't get everything. Because if I want to get 4, how many different pieces should I have? If I have 4 sets, how many different pieces should I have to count to number them all up? I should have 16 of them. But if I try and put another circle on this, I only get 14 actual pieces. So if I want to get all 16, I can't use a circle for set number 4. Remember I told you about the Venn diagram link on our Canvas page? I didn't get this on my own. I stole it from there. But I actually went through and counted them all. I have the outside. That's 0, 0, 0, 0. But then I have 1 through 4. I have 6 here. I've got 4 more here, and I've got 1 that's all of them. 1 that intersects all 4. A intersect D, A, C, D, A, B, D. I had to go through and count them really carefully. Every time you add another set, you double, just like every time you add another proposition, you double the rows on the truth table. I want to do 5. There's the 5th set. See how it winds back and forth around the 4th one? So it cuts in and out of everything else? Oh, hell no. I'm not going to ask you to make Venn diagrams of anything more than 3. But there are ways to do them where all of the shapes are the same. Just none of those shapes are circles. There's some very pretty pictures on that web link. You ought to go take a look. Questions? There are a lot of cases where I need lots of sets. As a matter of fact, one of the big pieces is the same idea we did with ands and ors. I can think about the union of a whole bunch of sets. Or the intersection of a whole bunch of sets. And then my De Morgan's laws will switch intersections and unions, just like they switch ands and ors. There are a lot of things in analysis, in the theory of calculus, that deal with exactly these ideas. And I am of the opinion that without a good understanding of how unions and intersections work, trying to do the stuff that is the reasons calculus works is completely impossible. So if you want to continue to understand why we do what we do in math, sets become an integral part, a necessary component of what we really want to do. And that makes it really easy to get lost in the weeds of all the different pieces and all the different parts and all the different places. So be careful when you're looking at unions and intersections in general, because there are a lot of very easy ways to get tripped up here. Okay. We finished 2-1 on Monday. We're finishing 2-2 today. That means 2-3 would be Friday. But what are we doing Friday? We're not meeting in person. So you'll be free from 12:30 to 1:30. If you usually have lunch before this, come down to the math competition in Sicilian Hall. I could use some help. 11:30, 12 o'clock to about 1. They have to be gone by 1, so I think we'll be done by then. Friday's lecture is already recorded. Notes and the lecture will pop up at 1 o'clock, midnight on Friday morning. I moved 2-1 to be due with 2-2 after the exam. So you don't have to do anything on chapter 2 until the exam's over. Exam is Monday. Wouldn't recommend waiting the whole time. It will leak out your ears. But that means 1-8 has just been turned in. I will post the key to that and the review sheet later this evening, so you'll have them to look at. If you look carefully at the top of the review sheet, what does it say? It doesn't. Crap, why didn't it say that? Hang on a second. It says it here. I want you to see this very carefully. The next to the last bullet, what does it say? I'm sorry, the next to the last bullet. This one right here. I did tell you it was a bunch of crap I didn't want you to memorize, right? You get to write it down. Important to note, there can be no worked out examples. Formulas, definitions, rules, one side, one page, handwritten. Okay? I will collect it with the exam. I will grade it. You will be penalized for inappropriate things on it. I will give it back to you. What happens when exam 2 rolls around? You get another one. By the time we get to the comprehensive final, don't lose these. I will see you all on Monday. Have a wonderful rest of your day.